The right one must be left. Straight ahead is never good at all.
Hi guys, my name is Nako Nakatsuka. I'm a fourth year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. Now let's talk about resonance structures. So some Lewis structures have multiple bonds in different equivalent positions. And so the definition of a resonance structure is basically three structures all having the same energy. And so in this case, let's do an example NO3 minus. So let's draw the Lewis structure of the nitrate ion. We have 5 valence electrons for the nitrogen. We have 6 valence electrons for the oxygen, and we have 3 of those guys. And we have 1 negative charge, meaning we have 1 extra electron. When you sum those up, you get a value of 24 electrons. So following the rules of drawing resonance structures, which we covered previously, we can draw this out as NO, where the only way for all 4 atoms to have an octet is to include 1 double bond. And in this case, I placed it right here. But this double bond can basically have 3 different positions. It could be here, it could be here, or it could be here. So now let's look at this first structure, which is exactly like what I drew up here. In this case, this double bond between the nitrogen and the oxygen is 1.2 angstroms, and this is the length of the bond. On the other hand, if we look at this same bond, but when it's a single bond, it's 1.40 angstroms. The reason why the single bond is longer in length than the double bond is because it's a weaker bond. The weaker the bond is, the longer it is, the stronger it is, the shorter the length. And so if this was a triple bond, it would be even smaller in terms of the distance between the nitrogen and the oxygen. So when we look at the nitrate ion, the observed nitrogen-oxygen bond length is actually approximately 1.24 angstroms. So that's actually closer to the double bond length. But the representation of the actual structure is a blend of all 3 structures that are drawn right here, where one has the double bond here, the other has it here, and finally there's another one like so. And each of these have a partial double bond character. And this blending of these structures is called resonance. And this is indicated by these double-headed arrows right here. So this is a typical way in which you draw resonance structures. But another way which I wanted to show you was if you draw out all the single bonds, but then you draw a dotted line indicating that for this particular molecule, the double bond could be in either one of these locations. Let me draw in oxygens. But in this course, you will more likely see this diagram. And so the resulting structure is called a resonance hybrid. And that makes sense because it's basically a hybrid of all 3 individual structures. So electrons that are involved in resonance structures are delocalized. And this is an important term, and I wanted to give you another example in which we see resonance. And this is benzene, which has the formula C6H6. And it's one of those common molecules where we often see resonance. And so benzene has 3 delocalized double bonds, as you can see here. Double bond, and double bond. And now we have 2 possible structures, where in this case we have, let's call this atom 1, 2, 3, 4, 5, and 6. So we have carbon 1, 2, 3, 4, 5, 6. And so the double bond here is between carbon 1 and carbon 2, then between 3, 4, and between 5, 6. But another potential structure is when you have it between 2, 3, 4, 5, and then 6 and the 1. And so in this case, the double bond right here has a length of approximately 1.34 angstroms, and the single bond right here has a length of 1.54. So like the nitrate ion that we just talked about, the double bond is shorter in length because it's stronger. And so since the experimentally observed carbon-carbon bond lengths for all of these structures is 1.39 angstroms. So again, closer to the double bond length, but in between these two values. And thus, the better representation is a resonance hybrid, shown right here. And so this is the hybrid. And each of these carbon-carbon bonds are now 1.39 angstroms. And so benzene is a resonance hybrid, and now I want to summarize this in 2 sentences. First, resonance is a blending of structures with the same arrangement of atoms but different arrangements of electrons. Secondly, it spreads the multiple bond character over a molecule and thus lowers its energy. And so going from these two structures and blending it into the hybrid actually lowers the energy of the structure.
To me, no one really